Okay, so in the last example, after doing all these Boolean operations, what we are left with, all the minterms except minterm 3. So if I would like to write the truth table of this, and my f function is 1 here, 1 here, 1 here, 0 here, 1, 1, 1, 1. So we could have also write this using Maxterm. F is equal to Maxterm 3, right? It is X or Y naught or Z naught. So as you see, minterm representation is the knot of the Maxterm representation, right? So it might be easier in this case just to represent this using Maxterm only. Right, so f is equal to 3, or it is also equal to with the minterms. So this is how we can represent the same function. So let's do one more example with the minterm and maxterms. So in this example, we are given this f function a or b not c. So what is the minterm and maxterm representation? So first of all, what we need to do, we need to add the missing variables to these terms. So for the first term, I need to add b or b naught and c or c naught. And for the second term, I need to add a or a naught. Right? So then we can do all these operations, and then we can find the final representations just like we did here. But let's do this example in a shorter way. So instead of adding all these terms, what I can do, I can write my truth table for this function and write all my possible inputs. So let's look at this case. You can see from the function if a is 1, f is 1, because f is given here, right? A or b not c. So I can directly write for ones here. And if a is 0, then f is given b not c. So if b is 0 and c is 1, b is 0 and c is 1, so this is the condition, then f is 1 and the remaining are 0. So from this truth table, then I see this is my m1, this is m4, m5, m6 and m7. So these are my minterms. So I can write for the minterms, my f is 1, 4, 5, 6 and 7. So for the max terms, so once you know the minterms, you can easily write the max term is given as 0, 2 and 3. So you can say my f is using the max terms m0 and m2 and m3, right? Or you can just say f is equal to m1, m4 or m5, m6 or m7. Okay, now we have seen up to now and, or and not functions. But these are not the only functions we have. So we have other logical functions, and let's see those functions. And we will review this using two variables. So if this is my two variable, then in this case I might have 16 different functions. So this is the f0 function where all the outputs are 0 for these input combinations. And I will call this f is equal to 0 function. So in f1 function, I will have all 0 for the first 3 lines, and I have a 1 for the last case. And this is what we have seen already. So this is the AND function. So f2 is 0, 0, 1, 0. So this is f is equal to x and y naught. So there is no particular name for this function. So f3 is 0, 0, 1, 1. So this function is f equal to x function because f3 is 1, 1 where the x is 1, 1. f4 function, so you can write this f is equal to x naught y. f5 function 0, 1, 0, 1. So this is f equal to y function. So f6 is an important function for us. 0, 1, 1, 0. We call this function an XOR function. Okay, and this XOR is, you can write it like this, x and y naught or x naught and y. f7 is 0, 1, 1, 1. So this is our OR function. We have seen this already. f8 is is also important. This is 1 0 0 0, and this is the OR NOT or NOR function. So this is f is equal to x or y not or not function. And F9 is this 1 0 0 1. This is also important for us, and this is called XNOR function. And F is given by x not and y not or x and y. So similarly you can write F10, F11, F12, F13, and you can see it yourself, but F14 is important for us. So 1 1 1 0. So this is the NAND function where f is equal to x and y not, and f15 you can see it's all 1, so this is the f equal to 1 function. So let's look at the new functions that we have seen here. So these are the important functions. Let's start with NAND. So this is the symbol for the NAND gate. So this is x y, and f is equal to x and y not, and this is the truth table for the NAND function 0 0 0 1 1 0 1 1, and it is 1 1 1 0. So we also seen a new function called NOR. So this is OR NOT. So for the NOT operation we are using these bubbles, right? And then in this case f is x or y not, and the truth table for this is 0 0 0 1 1 1 1 0 0 0. So in the NOR function it is 1 if the both inputs are 0, and in the NAND function it is 0 if and only if both inputs are 1. In other cases, if any of the inputs are 0, the output will be 1. The two other function that we are seeing is the XOR function. So in this case it is similar to OR gate, but we have an extra line at the back. So this is my F, and the symbol for XOR operation is plus inside a circle, and the long way of writing this function is x and y not or x not and y. So if I write the truth table 0 1 1 0. So this is XOR function, or you can also say this is exclusive OR. And what is important about this function is it is detecting if the inputs are different, right? If one input is 0, the other is 1, my output is 1. If my x is 1, y is 0, then my output is 1. So this is detecting if inputs are different. Okay, so, and if I need to draw this gate, so this is my exclusive OR gate using AND, NOT, and OR gates. Okay, and the final function which is important for us is exclusive NOR or XNOR function, or we can write exclusive NOR. So this is the gate representation for the XNOR. So this is how we specify it using Boolean function, and this is the truth table. So the importance of this XNOR is, as you see, it detects if the inputs are equal. So in a circuit, if you need to find out if the inputs are equal or not, then you can use this XNOR and XOR gates. Okay, so similarly I can represent this using AND and OR gates. So in this case, so let's write this f is equal to x not, y not, or x and y. So x and y is here, x not, why not? Okay, so this is the representation of exclusive OR using the AND, OR, and NOT gates. Okay, so now we will see universality of NAND gates. So what this means, I can implement any function or any gate using only NAND gates. So this is not true for the AND gate, for example. Using only AND gates, you cannot implement all the functions. This is also true for the OR gate. You cannot use the OR gate to implement all the functions. But NAND gate, and we will also see the NOR gate, we can, using NAND or NOR gates, we can implement any functions. So for example, let's try to implement the NOT gate. So this is my NOT gate, and what I am doing here is I am giving input A and getting NOT of A. So I can have the same using the NAND gate. So this is my NAND gate, And what I can do here, I can put both inputs A, and this will give me A naught, right? So this is how I can implement a NOT gate using a NAND gate. Let's see how I can implement an AND gate. So what I can do here, I can have a NAND gate like this, and to get an AND gate, I need another NAND gate to do the NOT operation. So this is a NOT gate, right? So I give both inputs to the same signal, and this is also NOT. So I have two NOT operations which will give me AND gate, right? So what will I get here? A and B. Similarly, I can try to implement an OR gate. So let's say this is my OR gate. So I will take an NAND gate first, like this. And what will I do? I will be putting two NOT gates at my inputs, right? So if I do this, this will give me then A and B. So, but of course, I need to convert these NOT gates to NAND gate. Basically, what will I do? I will get a NAND gate. So this will be an OR gate using 3 NAND gates. So this is my OR gate. So let's look at what we did. So I have A naught here and B naught here, and let's look at here what I got. A naught and B naught and naught of it. So basically, if I use De Morgan's rule, this will give me A or B. So this is correct, and we use this De Morgan rule to prove this is an OR gate. So why do we do this? Why we try to implement everything with a NAND gate, right? So basically, in some cases, you may not have any other gate, right? In some designs, all you have maybe some NAND gates, and you need to do some additional operation in your design, and then using only NAND gates, you can implement any functions. So it might be useful in some cases. Also, it is good to see how we can transform our functions from one way to another. Okay, now let's look at some conversion rules. So what we did here, we converted our gate, right? Let's see our conversion rules. So if I have an OR gate, and if I put two NOT gates to the input, it will not change my functionality, right? But now I take this part and I move my NOT operations to the output. So from De Morgan's rule, what happens? So this is an OR gate, right? So this OR gate will become, this OR operation will become an AND operation in the De Morgan's rules, right? If you apply NOT operation, right, this will become an AND operator, and we will have a NOT here. So this is basically what we got. If this is A and B, A, B, A or B, right? So this is A, B. So what we got here is A naught, B naught. So this is A naught, B naught, and naught of it, and this is A or B. So what we have seen, if we have inverters at the input or the NOT gates at the input, and if we carry it to the output, then what happens? OR gate becomes an AND gate, and we will have a NOT gate at the output. So this is one rule. So if we push the NOT gates from input to the output, the OR gate will become AND gate, and we will have a NOT gate at the output. So this is what will happen. So let's do a similar thing with the NAND gate, and then in this case we push the bubble or the inverter from output to the input. So this is basically equal to having inverters at the input, but now our gate become an OR gate. Okay, so this is also equal to two inverters or two NOT gates at the input, and we have the OR gate here. Right. So when we push the inverters or the NOT gates from output to the input, then the AND gate become OR gate, and then we have NOT gates at the input. So similarly, if I have a NOR gate, if I push this NOT gate to the input, then what will I get? I will get an AND gate and the two inverters at the inputs. Okay, so these are the conversion rules. So when you push the inverters from input to the output, the gate, if it is an AND gate, it becomes an OR gate. If it is an OR gate, it becomes an AND gate. So let's do an example. So given this F, A and B or C and D. So we need to implement this using only NAND gates. So let's first draw our schematic. So this is A, B, C and D. So this is our original implementation and I need to use only NAND gates. So I will be adding some NOT gates here without changing the functionality. So what can I do? I can put an inverter here and another inverter here. So using two inverters on the same line doesn't change my functionality. Similarly, I can put an inverter here and another inverter here. So I see this is a NAND gate now. This is also a NAND gate. And here for this one, I can push these inverters to the front and this will give me a NAND gate. So basically I can implement the same thing using 3 NAND gates. So this is A, B or C, D. Okay, let's do another example. So given this function x naught z or x y naught or x naught y or yz. And we are required to implement this using NAND gates only. So let's draw our schematic for this function. So this is my x, z, x, y naught, x, y, and y and z. So all of these will be ORed together. So this is my original schematic. Now I will be changing this to a NAND only. So previously, as we have seen, putting these inverters on the same line, it does not change the functionality. So this is a NAND gate, this is a NAND gate, this is NAND, this is NAND, and this is also a NAND gate, right? So I can push the bubbles to the front. So this will have a 4 input NAND gate. So this is also NAND gate. So only remaining is these NOT gates, so I can represent them using a 2 input NAND gate where the inputs are connected together. So these are also NAND gates. One final example with the NAND. So we are asked to implement F is equal to A, C and D or B and C naught using only NAND gates. So let's draw our schematic. This is my CD. So this is B. We have an AND gate here. A. So this is F. And this is my B and C naught. So what can I do here? I can put bubbles here. Right, so this is a NAND gate. And to make this gate to a NAND gate, I can put a bubble here. But to compensate this bubble, I need to add another inverter here. Now this is a NAND gate. So in this line I can put 2 bubbles. So this is a NAND gate. So to make this OR gate NAND gate, I need to put another bubble here and yet another one here. So this is a NAND gate now. So this is also NAND gate. So what we are left with, this NOT gate. So instead of this NOT gate, I can use a NAND gate where the inputs are connected. So this is a NAND gate and this is also NAND gate. So I can also put here. So now we have converted all of our gates to NAND gates in this example. Now let's see universality of NOR gates. Similar to NAND gates, we can implement any functions using NOR gates. So if I have an inverter here, I can do the same thing using a NOR gate. So this is the equivalent gate of the NOT gate using the NOR gate. So if this is A naught, so this is A, this will be A naught. So you can see A or A naught will give you A. So for an OR gate, let's say this is A, B, and this is A or B. So this is equivalent to a NOR gate, and we need to add another inverter here. So I can use a NOR gate here as well. So if this is A and B, so we got A and B here. So this is the equivalent gate of OR gate using 2 NOR gates. Let's implement the AND gate using the NOR gates. So I can represent this AND gate using 2 inverters at the input and AND gate here. So this is still an AND gate and this is equal to, so these are the inverters or the NOT gates. And if I push these to the front, then I will get a NOR gate here. So I have A and B here. So let's do two examples with the NOR implementation of functions. So in this example, f is given A or B, C or D, and E, and we are supposed to implement this function using NOR gates only. Let's draw our functions. So to convert the first OR gate, I can put a inverter here, but I need to add another inverter here. So I can put inverter here, another inverter here. So this is a NOR gate, this is a NOR gate. So to make this AND gate to a NOR, I need to put a bubble here and add another inverter here. Now this is a NOR gate. So this is also okay, and I need to put a NOR gate equivalent of the NOT. So now we have converted all of our gates to the NOR. And last example with the NOR. So we are given this F equal to A B NOT or A NOT B and C or D NOT. And then using only NOR gates, I need to implement this. So let's implement this. So to get the NOR implementation, I can put a bubble here and another bubble here. So this gate is okay. So to convert this AND gate, I need to put a bubble here and another bubble here. So this is okay. This is also okay because this is equivalent to a NOR gate. So to convert these AND gates, I can put some bubbles here. To convert the top AND gate, I can put two bubbles here, right? So I need to add an inverter here, and basically I move it to here so I can cancel this. Similarly, I can move it here and I can put two inverters for the B. So this is equivalent to a NOR gate. This is also equivalent to a NOR gate. So this is okay, this is okay. All we need to do is convert these inverters, and you can replace this using a two input NOR gates where the inputs are connected together. Similarly, we will be replacing this and replacing this with this, and we have converted all the gates to the NOR.